So welcome you back to today's lecture. So what I'm going to do today is I'm going to start a new topic, which is a decision theoretic formulation of estimation problem. So I'll give the name of the topic as Bayes and Minimax estimation. What does it mean? It will be explained in the due course. But let us try to do a recap of parametric estimation problems. So parametric estimation problem, so that you are on top of things. So the typical situation is as follows. You have a data x1, x2, xn. This is distributed according to some distribution function f, which belongs to a parametric family. Let me call this as P, f of theta, says that theta belongs to capital theta. Now in this case, form of f theta is known, functional form is known. But theta is unknown, right? So that is the situation. So like you have a normal distribution. So what you know is x1, x2, xn is a data which could be independent and identically distributed from a normal distribution with mean as mu and variance and sigma square. So mean and variance are unknown, but for the normal distribution, functional form of the distribution function or equivalently the PDF is known, which is nothing but 1 by sigma root 2 pi e to power minus half 2 sigma square x minus mu whole square. So that is a situation, a typical situation in a parametric statistical inference problem. Of course, non-parametric statistical inference problem, what happens is even the functional form of f theta may not be known. So what you have is you have a f which belongs to a family P. At the best, you may know that f is absolutely continuous. But we are not going to deal with non-parametric estimation problems over here. We are just dealing with parametric estimation problems. So the situation is as follows. And I'm interested in to estimate psi of theta, some function of theta, under the loss function L theta A, which, it's under L theta A. So suppose D is, we define what does it decision rule means. So D is a class of all decision rules, which includes even randomized decision rules. And how did we define as a randomized decision rule? A randomized decision rule is nothing but a probability distribution on the xn space. So my xn space over here is nothing but all possible values of psi theta such that theta is in theta. Because I want to estimate psi theta, so my xn should be some value of psi theta. So a randomized decision rule is nothing but a probability distribution on the xn space A. So what do you do in the randomized decision rule? After the data has been done, you don't immediately take the xn. You do another randomization through a probability distribution on A, and whatever is the output of that random experimentation, that you take as your final xn. Non-randomized decision rules are particular cases of randomized decision rules where the probability distributions are degenerate on A. That means for every x, delta x takes only one value in A with probability 1. So there is no further randomization in that sense. So what I do is I denote the risk function r theta delta. So risk function of an estimator r is defined to be expected value of L theta delta x, which is basically nothing but expected value of L star theta x and delta. Now each, this corresponds to a probability distribution, so you can write down here as the final decision is your random variable, so this you can replace by y of x. Okay, so what you try to do is this risk function depends on theta. So the question arises, can I find a decision rule or an estimator for which this risk is minimum for every theta? Does there exist a delta star such that R theta delta star is always less than or equal to R theta delta for every theta belonging to theta, and for any other decision rule delta belonging to dm? So that is the question. And the answer is no. Why? Because R theta delta is a function of a theta. Minimizing a function over all parametric points, theta will not be possible. As I told you, you can always consider your estimator to be a constant estimator. Let us say if you are estimating a normal mean, you always estimate mean by 1. So what is the risk of estimator which always estimates mean by 1? Theta minus 1 whole square. There is no randomization, so it is just theta minus 1 whole square under square error loss function. So at theta is equal to 1, this minimizes the risk, because at theta is equal to 1, the risk becomes 0. So at minimizing risk at particular point is done by trivial estimators. So minimizing at every theta will not be possible. So then what you try to do? You try to put certain reasonable restrictions on the class of estimators under consideration. So you restrict D by imposing certain restrictions or some other criteria which you use to eliminate estimators in D. Of course, one thing we saw that if L theta A is convex in A, then it is enough to consider only non-randomized estimators. But non-randomized estimator itself is a big class. So can I further restrict this by putting certain reasonable restrictions? Now that depends on the statistician what conditions he thinks to be reasonable. Two different statisticians might have a different requirements, and they might feel they want to put different restrictions to restrict this class of estimators D. So what do you do? So in the last course you saw that I would expect any estimator to be unbiased. That means if I use it over a long period of time, on an average, it should give me the true value of the estimate. That means my estimator should be such that expected value of delta x is same as psi theta. Now if you put that restriction, then class of all estimators under consideration gets restricted to a large extent. For example, all constant estimators get eliminated because expected value of a constant estimator 1 is 1. It cannot be psi theta for every theta, because psi theta is a function which would keep varying. So all constant estimators are eliminated from consideration. So one set of possible restrictions which we saw, so restrictions for restricting unbiasedness. And then you saw that the moment I put a restriction of unbiasedness, and if I'm considering a square error loss function, then the risk is same as the variance. And then we saw that in certain situations, it is possible to find the estimator with the smallest risk. So in this case, risk is the same as variance, and it is possible in certain situations to find UMV-UE, uniformly minimum variance unbiased estimator. The other restriction which we started in this course is applicable in certain situations where the estimation problem under consideration has a nice structure, in the sense that your estimation problem is invariant under a group of transformations. So the second reasonable condition which we studied in this course was principle of invariance. Through principle of invariance, what you do is, if your estimation problem is invariant under a group of transformations, then you consider only invariant decision rules. And then you see that when you consider only invariant decision rules, in certain situations it is possible to find the best rule. So minimum risk invariant estimator exists in certain situations. Even in situations where UMV does not exist or minimum risk invariant estimator does not exist, at least by imposing these restrictions, you have restricted your class of estimators under consideration. So a lot of unreasonable estimators, as per your judgment, are out of consideration. So you have dealing with a smaller class of estimators, and so what you would have is you have a class of competing estimators. And within the class under consideration, you can choose the estimators which should be considered as competing estimators, and then you restrict only on those estimators. Now let's look at what are the other reasonable things we can think of. So if you recall, the real culprit is that your risk function is a function of theta. And minimizing risk function for every theta is a problem, because the class of estimators under consideration is too big, and then you have a lot of undesirable estimators like a constant estimators which only minimize the risk at only one point. No other estimator can perform better than that constant estimator for that parametric value. For example, if your constant estimator is estimate the mean only by 1, then at the parametric point 1, no other estimator can have a smaller risk than this constant estimator. So it does nothing. It only gives you a very favorable situation at one parametric point. And that parametric point, number of parametric points are uncountable, whole real line. Minimizing it at only one point, and then it just spoils the whole game. So you try to put restrictions on class of estimators so that all these kind of undesirable estimators like constant estimators get eliminated. So you did unbiasedness and principle. The second thing I realize is the real culprit is theta. So that rather than considering the risk function, if I consider some characteristic of a risk function which does not depend on theta, then that means I am dealing something which does not depend on theta, that means that is a constant. And then I can think of finding an estimator delta for which that constant is minimum. Now, I explained to you before, a statistical decision problem can be considered as a game between a statistician and a nature. Nature is unknown, which is basically this theta or this psi theta. statistician is trying to guess what is the true state of nature. And how does he do that? He tries to conduct some experiment, obtain certain data, and based on that data, he tries to guess what is the true state of a nature. So in many situations, what might happen is the statistician from his past experience may have certain information about the true state of nature in different situations. And he may be able to use this information to quantify this information in terms of a probability distribution. Because that is what you have information, you can always construct a probability distribution based on your prior information. So what I have is, I have some prior information on this theta. So let us consider that situation. And then what happens is, if I have a prior information on this theta, then rather than considering r theta delta, I may consider the average risk. Because theta is random, I can talk about the average risk. And this true state of nature I have modeled through my past experiences. So that sounds pretty good. If you have a past information about the true state of nature, you try to quantify that in terms of a probability distribution. And then rather than considering the risk function, you try to consider the average risk function. And then try to minimize that average risk function, because once you have taken an average, it does not depend on theta. So consider some characteristic of r delta theta. So sometime I am denoting risk by r theta delta or r delta theta that does not depend on theta. Suppose some prior information is available about theta in the form of a probability distribution, because you had information about the state of nature, probability distribution. Making histograms and so on, you try to quantify that information in terms of a probability distribution. Or in other words, this true state of nature theta is considered as a realization of some random variable. Let me call that as S. Or in other words, true state of nature is a realization of a random variable as having given probability distribution, having known probability distribution. Now this probability distribution I call as a prior distribution. So suppose pi is the prior distribution. So when I say it is a prior distribution, that means pi is a probability measure. So what I do is, rather than considering r delta theta, I consider its average with respect to pi. So I consider on theta r delta theta d pi theta. So r delta theta was the risk which depended on theta, but theta has a probability distribution pi theta, so I consider the average risk, and I denote this by R delta with respect to prior distribution pi. So, which we call as base risk. This is called risk, usual risk or frequentist risk, R delta theta. Frequentist risk means it only depends on, it is constructed using just the data you have. Now, this base risk does not depend on in fact, it is a constant. It only depends on that prior distribution which you have considered and that is known to us. So, it may be possible to minimize this characteristic of the risk function which does not depend on theta. So, any estimator which minimizes this characteristic is called a Bayes estimator. So, let me write down definition. Let pi be a given prior distribution. Prior distribution means a distribution about the unknown state of nature. An estimator delta pi is said to be Bayes under prior pi if it minimizes this quantity. That means R delta pi pi should be the smallest among all R delta pi's as you vary data. So, if R delta pi pi is same as infimum over all decision rules D of R delta pi. Now, this in certain situations may be possible. In fact, in most of the situations you may be able to find the Bayes decision rule or the Bayes estimator under a prior pi. Now, note that I have put a pi over here just to emphasize the fact that a Bayes estimator depends on what prior you are considering. As you change the prior distribution, your Bayes estimator changes. Good. So, this is one characteristic, that you try to minimize average risk rather than minimizing the risk at every theta, which is not possible. You try to search for an estimator which minimizes the average risk, and you call such an estimator to be average estimator, sorry, Bayes estimator. Now, one may also think of minimizing the maximum risk. So, it is like saying that, look, I want to play safe, and I want to minimize the maximum loss which might occur to me. Or equally, I try to minimize the maximum risk which occurs to me. So, it is like this, you go to a casino with friends. In first half an hour you have made good enough money and you are satisfied with that money and you want to create a status quo. The option with you is you can leave the casino by making that much money, but then it may not look very nice because you have come all with all the friends and all friends would feel cheated that, look, this fellow made money in the first half an hour and then our friendship got over the moment he made money. So, you would like to stay for the sake of your friendship in the casino, but still you are happy with the money which you have won. You don't want to lose it further, but you have to also play for the sake of playing it. So, what should be your strategy? That, look, I don't now want to minimize my average loss. I try to see what is the maximum loss which may occur to me. Maximum loss would be all the money which I have made so far. That goes away, which I don't want to happen. So I want to safeguard that worst scenario. So one may think of minimizing the maximum risk. You see, minimizing the minimum risk is not possible because, as I said, you can always consider the constant estimator. For the constant estimator, minimum risk is 0 because you have to only minimize it at only one point. So minimizing the minimum risk is so many estimators. All constant estimators are minimizing the minimum risk at a particular point. So another characteristic of risk function which is independent of theta is you try to look at the supremum of the risk function and try to look at estimator which minimizes the maximum risk. And you call such an estimator to be the minimax estimator. An estimator delta naught is said to be minimax if it minimizes the maximum risk. So that means the maximum risk of delta naught, which is supremum theta belonging to theta of R delta naught theta. So that is the maximum risk of delta naught is the smallest among all estimators. So that is same as infimum over delta belonging to delta of all maximum risks. So supremum theta belonging to theta of R delta. Now note that once you take the supremum does not depend on theta. It is a constant. And it may be possible to find an estimator for which that constant value is minimum. Now, again I said one may say why you are talking about minimax. Min stands for minimum, max for maximum, so which minimizes the maximum. One may argue, can we talk also about, does talking min make sense? Min. That means minimizing the minimum risk. Now look, I have seen for any constant estimator, minimum risk is 0. So any constant estimator minimizes the minimum risk. So you don't get anything meaningful if you try to. So min doesn't make any sense. Because for all of them, the minimum risk is 0. Okay. So these are the two characteristics of the loss function or the risk function. One is the average risk or the base risk. Another is the maximum risk, which make the risk independent of theta. And then one may think of finding an estimator for which this characteristic is minimum. Or one may try to minimize this characteristic among all estimators delta.